Hoover High Honors Chemistry, this is Lesson 6, Periodic Trends. Okay, so previously we said similar charges repel and different charges attract each other. These are called Coulomb forces. So there is a simple law of that measures the force in newtons of Coulomb's force. And it is F sub E, which is the electronic or electrical or electrostatic force, is equal to a constant called Coulomb's constant, K, times the first charge times the second charge divided by the distance between them squared. This formula may look somewhat similar to a formula you saw in physics related to the force of attraction between two objects with mass that used the universal gravitational constant G. It's set up exactly the same way because both of them are forces, gravitational force and electromagnetic force, and they behave similarly. But there's different variables in them. Alright, so Fe is the force between the two charges. Q1 and Q2 are the magnitude, the amount, in other words, of the charges. D is the distance between them, and the Coulomb's constant. Of course, you never have to memorize constants, but there it is. The most important thing when you look at a constant like that is look at the units of measure. And this is in newtons, and newtons are expressed in kilograms times meters per second squared. And then you have meters squared up on the top in the units of measure here, and you have coulombs down on the bottom squared. And the reason it's important to look at that is because it means that all of your units in this problem have to be in those units that make up the constant. For example, if you were given a distance in nanometers, you would have to convert that into meters because this constant is not expressed in nanometers, it's expressed in meters. So you have to be sure that you make all of the constants of the distance and of the charges line up so that you can use this constant and it will you'll get the right answer. So there we go. That's just a quick review of what we saw in an earlier slide. Positive charges repel each other, negative charges repel each other, but a positive and a negative charge will attract each other. So almost everything that happens in chemistry is the result of Coulomb forces. Okay, so let's take a sample problem here. So what is the Coulombic attraction between a proton, and there's the charge on a proton that we saw in an earlier lesson, and an electron? There's the charge on an electron, the same as the charge on the proton except opposite, it's a negative, and they're separated by 0.7 nanometers. So that 0.7 nanometers we're going to have to convert into meters somewhere during the problem in order to be able to use the Coulomb constant. So there's the formula. And so look at this and compare what got plugged in where. Okay, you have the Coulomb constant out in front, and really it's in the numerator, it's up on the top. And then you have the two charges up on the top, and then on the bottom you have that you have the 0.7. I changed it to 0.71 for significant figure reasons, but don't worry about that. 0.71 times 10 to the minus 9th meter. So 0.71 nanometers is 0.71 times 10 to the minus 9th meters. Go back to that table that's in your reference sheets that shows you that nanometers is equal to 10 to the minus 9th. So you just replace the n, the nano part of it, by 10 to the minus 9th, and then it's meters. Okay, now doing the actual arithmetic on this can be a little tricky. You have to be careful. So first you multiply all the coefficients. And so it's 8.99 times 1.602 times negative 1.602, and then you divide by 0.71, and you have to square that. And PEMDAS calculator will do things using orders of operations. The PEMDAS will square the 0.71 first, and then it will do all the other operations. Another way to do a square like that is just divide by 0.71 and then divide by 0.71 again. That's the same as 0.71 squared. Anyway, that gives you 45.7686 for your coefficient. Then the exponents, and again, you have to be careful on this. You add everything on the top and you subtract everything on the bottom. So it's 9 plus negative 19 up on the top. That would get you to negative 10 plus negative 19 again. That will get you to negative 29. All right, and then down on the bottom, remember that the principles of exponents say that when you have that 10 to the negative 9th squared, you multiply those two numbers. So minus 9 times 2 is negative 18. And that would get you a negative 18 on the bottom. But a negative 18 on the bottom, again, another principle of exponents, so you have to understand these from math class, is if there's a negative 18 exponent on the bottom, that's the same as plus 18 up on the top. So you change the sign and move it up to the top. So it's 9 minus 19 plus 18 gets you to negative 11. Okay, so again, don't know how to do the problem, but stumble over the basic math here. Be sure you understand your principles of exponents. All right, and that gives you, we round the 45 to 46 because of significant figures. That's why I added the 1 to the 0.71 in the problem to give you two significant figures, times 10 to the minus 11th. All right, and now you have to adjust the decimal. The decimal is after the 6 and 46. You need to make it a number between 1 and 10, so you move the decimal over between the 4 and the 6. So you made the coefficient smaller, going from 46 to 4.6. Therefore, you have to make the exponent bigger. So that goes from negative 11 to negative 10. And the final answer is 4.6 times 10 to the negative 10. Okay, let's get into Z numbers and Z effective. Lithium has an atomic number of 3. Again, if you look on the periodic table, and every time you do chemistry, please have a copy of the periodic table in front of you. You're going to use it every minute of every day in this class, so be sure it's in front of you. So lithium has an atomic number of 3. The atomic number is called the Z number. The atomic number is the number of protons in the atom of an element. So if we look at lithium, there it is. That yellow box will show you the way it will appear on your periodic table. So atomic number at the top is the number of protons. Li is the abbreviation for lithium, then the name lithium in English. In the English language, we call it lithium. And then 6.94 is the atomic mass. That's the average mass of all the different isotopes of lithium. They average out to 6.94. So we see it has a Z number of 3. That's the atomic number at the top there. The core electrons are the electrons inside of the valence orbital. The core electrons are said to screen or shield. Those words are used interchangeably. Some books use the word screen, some books use the word shield. They're said to screen or shield the valence electron from the pull of the protons in the nucleus. So remember, negatives repel negatives. So those electrons are repelling each other. The two that are in the first orbital, they can coexist in the first orbital. That's not a problem. And the third one is in the second orbital. But what they're doing is repelling that outside orbital. The two on the inside, the two core electrons, are repelling that outside valence electron. So normally that valence electron, an electron would feel the pull, the attraction of 3 protons. But because those two core electrons are standing in between the protons, the plus signs, and that valence electron, it doesn't feel the pull fully of those 3 protons. And by the way, these electrons are buzzing all over the place. It's not like they're all just static, they're just sitting there. However, the fact that those two core electrons are buzzing all around inside of that valence electron, it will create this shielding effect. All right, so how do we figure out how much pull that valence electron is feeling? And that's important because it will determine how much energy is required to take that valence electron away from this atom. So core electrons are all electrons inside of the valence orbital. These electrons screen the valence electron from the pull of the protons. Valence electrons are electrons in the outer orbital. The effective Z number, which is just abbreviated Z effective, that's how you would read that, Z effective, or you could say it's effective Z number, measures how much of the pull of the protons an electron feels. And it's a very simple formula. Z effective equals the Z number minus the number of core electrons. So it's the number of protons pulling on that electron minus the number of core electrons that are in between the nucleus and that electron. So in this case, for lithium, it would be 3, that's the Z number for lithium, minus those 2 core electrons would equal 1. So although lithium has 3 protons, its valence electron feels the effective pull of only 1 proton. That means it's not being held nearly as tightly to that atom as it might seem having 3 protons. So that's what effectively it feels. I took away the core electrons, and now you see that 1 valence electron and only 1 proton in the nucleus. The other 2 didn't really disappear. What we're just saying is that that's effectively, it only feels as though it's being held by 1 proton. Okay, ionization energy, a very important term in chemistry. You're going to hear it, if not every day, pretty close to every day. So ionization energy is the amount of energy that is required to pull an electron from its atom. The man represents ionization energy. The ionization energy must have a greater pull on the electron than the protons do. So in other words, he's pulling on that electron, and the protons are pulling that electron in. They're trying to hold that electron in that atom. So where does the ionization? It's not really a little man, so what is it? It's the attractive pull of another atom or another ion that's pulling on that electron that wants to pull it away from this atom. And if it's stronger than the pull of the protons, which the Z effective is only 1 in the case of lithium, then it will leave the lithium atom. Lithium is one of the easiest elements to ionize, to pull that outside electron away from, as we'll see coming up. So ionization energy is also called electron binding energy. We tend to use the term ionization energy. Technically, ionization energy deals with a gas molecule, gaseous molecule, that is just an independent floating molecule, whereas electron binding energy deals with an atom, I said molecule, an atom that is in metal. And we're almost never going to use the term electron binding energy. Okay, so ionization energy increases to the right across the periodic table. So let's just take the second row, lithium, beryllium, boron, all the way across to neon. The ionization energy increases. Lithium has the lowest in the second row, and neon has the highest ionization energy in the second row. It also increases going from the bottom to the top of the periodic table. So if we look at the first column in the periodic table, francium down at the very lower left has the lowest ionization energy. It's easiest to pull an electron away from it. And lithium up second in the first column, Li, has the highest in that column. And hydrogen actually a little bit higher. Hydrogen's kind of an oddball. It doesn't really belong in that column in some ways because it's a nonmetal, but it would also have a high ionization energy. So ionization energy increases. So in general, the lowest ionization energies, that is the ones that are the easiest, the atoms that are easiest to pull an electron away, are in the lower left side of the periodic table. You see CS, Ba, Ra, Fr, those would be the easiest to pull an electron away from because they have the lowest ionization energy. And the upper right side, that would be helium, neon, fluorine, chlorine, everything you see in the upper right, those would be the most difficult. They have the highest ionization energy, and therefore it's the most difficult to pull one of their electrons away from them. So ionization energies increase up a group, that's up a column, and right in a period. That is from left to right in a row. So here's kind of a perspective view of it. Ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. So that gives you kind of a visual idea of the ionization energies. Lowest ionization energy in the lower left, highest ionization energy in the upper right. So now let's be able to explain that. Sometimes the explanation is a little easy, and sometimes it might require a little thought to understand it. So ionization energies are lowest when an electron is furthest away from the nucleus, that is, has the most orbitals, and the nucleus has fewer protons. All right, so let's look at lithium, and let's look at the second row, that row there that starts with lithium and ends with fluorine over on the right. And actually the next row over would have been noble gases, but I'm going to use the halogens, the second to last column in this example. That's fluorine. So let's compare lithium to fluorine, number 3 to number 9. Lithium has a lower ionization energy for its electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's electrons. That's the key point. They both have 2 orbitals because they're in the second row. So lithium only has 1 electron in the second orbital, whereas fluorine has 7. But the fact is, those 7 fluorine electrons are the same distance away, they're in the second orbital, as the 1 lithium electron, which is also in the second orbital. It's the same distance from the nucleus as fluorine's electrons, but it has only 3 protons to attract it, while fluorine has 9 to attract its electrons. So fluorine has more electrons pulling on those, more protons in the nucleus pulling on those 7 electrons than lithium has pulling on its 1 electron. Now you might ask, well, doesn't the fact that fluorine has more electrons matter? And the answer is really no, because when you look at the diagram there, that small diagram of the fluorine atom, those electrons are side by side. They're not blocking each other. And so the protons can reach out and pull all 7 of those electrons in very, very hard. Because they're not blocking each other. They're all the same distance away. They're side by side effectively. So you look at lithium on the left and the fluorine on the right. Now let's compare going up that column that has fluorine on the top and bromine down below. And how does ionization energy, how does it trend there? So bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther from the nucleus. And I should add, it's because they have a lot more core electrons. Look at how many core electrons are in between those outside valence electrons in bromine and the nucleus. There's a whole lot of screening or shielding going on there. So you might ask, but doesn't bromine have a lot more protons? Yeah, it has 35 versus 9 for fluorine to pull those valence electrons in. So this seems to contradict the rule we learned just a minute ago for lithium to fluorine. However, in this case, it's the orbitals and the core electrons that predominate over number of protons. So when you're looking up and down in a column, it's how many orbitals. When you're looking side to side, it's how many protons. So you just have to remember it's kind of 2 different rules for each of those. So if you look at that diagram of bromine, look at all the core electrons it has inside of the valence shell that's blocking those valence electrons from feeling the pull of the protons, even though there's a lot of protons in bromine. So therefore, it has a lower ionization energy, bromine does. It's easier to pull bromine's electrons away from it than it is to pull fluorine's electrons away from it. So fluorine has a higher electronegativity than lithium or than bromine. Now electronegativity. Electronegativity is very much related to ionization energy. So the man represents electronegativity. So now he represents the pull of the protons. And what he is doing is what electronegativity wants to pull in an electron from the outside. So both ionization energy and electronegativity have to do with pulling electrons. But electronegativity is pulling in an outside electron, an electron that didn't otherwise belong to it. Whereas ionization energy has to do with how much energy it takes to pull an electron away from an atom, or another way you could express that is how much do the protons hang on to their own how much do the protons in a nucleus hang on to the electrons in that atom. In other words, how much do they want to pull in on their own electrons. So ionization energy has to do with holding on a nucleus, the protons holding on to its own electrons, versus electronegativity is how much do those protons want to pull in an electron from the outside. And there it goes. So electronegativity is measured on a scale of 0 to 4 called the Pauling scale. Fluorine has the highest electronegativity of 4.0. So electronegativity increases as you go up a group and right in a period. So the trend is the same as ionization energy, as you might expect, because as we said, they just both have to do with pulling in on electrons. If we take lithium and fluorine again, lithium has a much lower electronegativity. It doesn't do very good. It doesn't do a very good job of pulling in outside electrons. And fluorine has a very high electronegativity, the highest on the periodic table. It does an excellent job of pulling in electrons from the outside. In other words, electrons that belong to other atoms. Similarly, going up the periodic table, fluorine is higher than bromine or anything in its column. So it's the same trend as ionization energy. So electronegativity is greatest in the upper right-hand corner of the periodic table where fluorine is. So you notice this looks very much like the perspective view that we just showed of ionization energy. Lowest electronegativities are in the lower left. Highest electronegativities are in the upper right. The elements on the right side of the periodic table are called noble gases. Noble gases have no electronegativity. We will learn the reason for this later. So you notice this perspective view, you don't see the noble gases there. Helium, neon, argon, krypton, and so forth. They're not there. The first column, the furthest column on the right you see are the halogens: fluorine, chlorine, bromine, iodine, on down. So that noble gases do not have electronegativity. They have very high ionization energy. It's hard to pull electrons away. However, they don't want to pull in outside electrons at all. And we're going to learn the reason for that. So lowest electronegativities and highest electronegativities. Noble gases are not shown because they have no electronegativity. Okay, electronegativities are highest when there are fewer orbitals and the nucleus has more protons. So if we look at lithium, lithium has a lower electronegativity than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull in outside electrons as well as fluorine. Bromine has a lower electronegativity than fluorine because bromine has more orbitals and more core electrons. The electrons are screened more from the nucleus, so it can't pull in outside electrons as well. Remember, what we're talking about here is how well can those protons reach out past its own orbitals and its own electrons to grab an electron from the outside. And fluorine does it better because it has more protons while having only 2 orbitals. Lithium has only 3 protons and 2 orbitals, so fluorine is better at reaching out with those 9 protons to grab outside electrons. Bromine has trouble grabbing outside electrons. In fact, it really doesn't do it at all because it has to reach past 35 electrons of its own to get an outside electron to grab it and to pull it in, and it just doesn't do that very well. So fluorine has the highest electronegativity on the periodic table of any element at 4.0 on the Pauling scale. Atomic radius is half the distance between the nuclei of 2 bonded atoms. It is roughly the distance from the nucleus of an atom to the valence electrons. In other words, you can think of it like the radius of a circle in geometry. The radius of a circle is from the center of the circle to the perimeter of the circle, out to the circle. and that's the radius of a circle, and the radius of an atom is pretty much the same. It's a distance from the center to the outside. But the way it's formally defined is as shown here. The half the distance between the nuclei, the nucleuses, you want to say it that way, of two bonded atoms of the same type. Atomic radius is important because some chemical properties depend on whether an atom can fit into small spaces. So there will be times when we talk about the atomic radius, it has to do with bonding strength between different atoms. It has to do with something called dipole moment. So we'll talk about that at a later time. So atomic radius decreases as you go up a group and right in a period. So notice that this is the opposite of ionization energy and electronegativity. As you go left to right, the atomic radius, in other words, the size of the atom, decreases. And as you go from bottom to top, it decreases. Now, one of those is kind of obvious why, the other one not so much so. So let's talk about that. Atomic radius are highest when an atom has more orbitals and the nucleus has fewer protons. So lithium has a larger atomic radius than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull electrons as well as fluorine. So what that means is that this is kind of strange because lithium has 3 protons, the most common isotope has 4 neutrons, and it has 3 electrons. That's a total of 10 particles, 3 plus 4 plus 3. Fluorine has, the most common isotope, has 9 protons, 10 neutrons, and 9 electrons. So that's a total of 28. So fluorine has almost 3 times as many particles as lithium, and yet it's smaller. In fact, it's much smaller than lithium. Why would that be? It has all those particles, but it's smaller. And the answer is those 9 protons in fluorine pull much harder on its electrons, its own electrons, and pull them in. So it makes the nucleus tighter. It makes the atom tighter and smaller. Whereas lithium's 3 protons, which we've said already is only an effective, Z effective of 1 proton, doesn't pull very hard on its outside electron or its other electrons, and therefore it's larger. They stay farther away. So again, it's kind of a paradox that even though lithium has far fewer particles than fluorine, it is much smaller. So be sure you understand that explanation. Fluorine in the upper right corner has the smallest radius of these elements that you're seeing right here. Bromine has a larger radius than fluorine because it has 4 orbitals compared to only 2 for fluorine. That's kind of an obvious explanation. The more orbitals, the further out the electrons get. So an atom with more orbitals is going to have a larger radius. It's going to be bigger than one with fewer orbitals. So that why bromine has a larger atomic radius than fluorine is kind of obvious. It's just more orbitals. It's the one going across from lithium to fluorine that doesn't seem to quite make sense. Why would fluorine with more particles in it be smaller than lithium? And it's because fluorine really pulls all of its electrons in very tightly because it has so many more protons than lithium. The second period elements show that lithium is much larger than neon. So this one goes all the way across from lithium all the way to neon, the noble gas there. Look how much smaller neon is. You can barely see it. It's number 10 in the second row. That's the end of the second row. And lithium, look how much larger lithium is than either fluorine or neon. So it's not a small difference. It's a really big difference between the size of lithium and the size of fluorine or neon over on the right side of the second row. This is due to the fact that both lithium and neon have 2 orbitals. However, neon has 10 protons pulling on its second orbital, while lithium has only 3 protons pulling on its second orbital, and therefore neon pulls in its electrons much more tightly and much closer than does lithium. So as we move to the upper right-hand side of the periodic table, ionization energy, electronegativity increase while the atomic radius decreases. Why? So be sure you can explain the why that is. So those arrows, ionization energy from left to right increases, electronegativity increases, atomic radius decreases from left to right, and going from bottom to top, ionization energy increases, electronegativity increases, and atomic radius decreases. So have those memorized. Know those trends. So as you go across a period row, more protons are added to the nucleus. The electrons are pulled in with greater force. This means the atomic radius becomes smaller. The energy required to pull an electron out, ionization energy, becomes greater, and the ability to pull in an electron from the outside becomes greater as well. As we go down on the periodic table, more orbitals are added. This makes the atomic radius larger, so we're going from top to bottom now in describing this, and the outer electrons are farther from the nucleus. This increased distance makes both ionization energy and electronegativity less, because those outside electrons are not being pulled on as hard because of the increased number of orbitals and shielding electrons. So look at this chart. You should understand how to read this chart. It measures the atomic number on the horizontal or x-axis. And so it just goes from 0 all the way up to 110. The largest natural element is uranium at 92. And then the vertical axis, the one going up, measures the atomic radius in picometers. That's a very small number. That's 10 to the minus 12th. It's 1/1,000,000,000th of a meter. And so it's measuring the atomic radius in picometers going up from 0 to 330 picometers there. So that first dot in the lower left represents either hydrogen or helium, or it's just both of them on top of each other. I'm not really sure. But then the yellow dots are the second row. So the one at the top is lithium. Lithium has the largest atomic radius. If you were to guess, you'd say it's around 170 picometers. Then as you go from left to right across the second row, the atomic radius gets smaller. So the next dot down, the next yellow dot down from the top is beryllium, and then boron, and then it goes all the way across to where the very bottom yellow dot there would be neon. Now, as you add a third orbital, everything gets pushed out, all the electrons in the third orbital, of course, farther away. So now you jump all the way up to that top red dot, and that would be sodium, Na. That's the first element in the third row. And then down from that, magnesium, and then all the way across the third row until you got to argon. That would be the bottom dot there. Then the fourth row is the light blue dots, and now you notice something about those. There's a lot more of them, and that's because you have the transition metals down there. That's that valley on the periodic table, and that's the first row that actually has those transition metals, so you see 18 dots there. Similarly for the fifth row and sixth row as well. And the sixth row actually includes even more. It actually includes some of the elements from down in the on the bottom of the periodic table. We're not going to get into talking about those. So the radius increase with each row because an orbital is added. The blue, brown, and green columns have 18 dots because there are 18 elements in these rows. Now we're going to talk about a couple of experimental techniques. One is mass spectrometry. And it's also sometimes called mass spectroscopy, and it's a way of determining the mass of an isotope. It works on the principle that a lighter atom or isotope can turn faster than a heavier one. So look at this truck and this motorcycle. If they're going down a road at the same speed and they suddenly have to make a right turn, the motorcycle will be able to turn faster or sharper because it's lighter. So there you see it right there. The truck can't turn quite as quickly because it's much heavier. And this goes into Newton's law of inertia. If a truck and a motorcycle turn a corner, the lighter motorcycle will turn quicker than the heavier truck. So lighter isotope atoms curve quicker than heavier ones. So here's actually an image of how it works. Mass spectrometry is a way of determining the mass of an isotope. So remember, isotopes have the same of the same element have the same charge, but they have more. One has more neutrons than the other, and so one is heavier than the other. That's the main difference between isotopes, and it works like this. The isotope atom is ionized, so it has a charge. A magnet moves the isotope through a tube. So a magnetic field moves the isotope atoms through a tube. It's kind of like, in a way, kind of like Rutherford's, or J.J. Thomson's rather, cathode ray tube. However, this is not electrons. This is isotopes of atoms. So what they have to do is they have to ionize it so that it does have a charge and therefore can be deflected by a magnet. But they're not interested in the charge on it. They're interested in the mass of the isotope. And then 3, the isotope atom passes through a perpendicular magnetic field. So this perpendicular magnet causes the isotopes to curve. And how much the isotope atom curves determines its mass. A heavier isotope will take longer to curve. So heavier isotopes curve the least. So the heavier isotopes would be the one, if you see that tube there, they would be the ones toward the top of the tube. And you can see the line where they graph it over there. Relative abundance simply means how many. And then the M per Z is the mass per Z charge. So it's a ratio of the mass to how much charge it has. And you can see that the heavier isotopes are farther on the right on that table. The lighter isotopes are the one that would be in the bottom of the tube there where the arrow is pointing, and they would be on the left side of that table. So they would have a lower mass to charge ratio, less mass, in other words. It's just the way to think of that. Okay? All right, so that's how mass spectrometry works, and we're going to see a video about mass spectrometry in class this week. Photoelectron Spectroscopy, PES, is a way to determine the ionization energy or binding energy of an electron. So how do they measure ionization energy? This is the method they use. The ionization energy or binding energy is equal to the energy of the photon minus the energy required to make the electron travel a certain distance. So the following formula gives the binding or ionization energy. So the ionization energy equals the energy of a photon of light. Now a photon, we haven't gotten into that concept, but it's the energy in basically a particle of light minus the energy that it takes to make an electron move a certain distance. So let's think about that before we even read any further. If I put, well, actually I'll give a numeric example here, so let's just go to that and then we'll talk about that. So here's electron number 1. It's the valence electron in a lithium atom. I've excluded the neutrons because they're not important here. So assume that a 20 kilojoule photon, so it's a particle of light that has 20 kilojoules of energy. Energy is measured in joules. And it strikes that electron. And let's say that electron flies a distance that requires 15 kilojoules of energy. And they, how they measure this is beyond what we need to understand for this class, but they have ways to measure this. So E kinetic, that's the energy of motion of that electron, is 15 kilojoules. That's the kinetic energy required to make the electron, electron number 1 travel this far to wherever that arrow is going to. So here's electron number 2, and assume 20 kilojoule photon then strikes electron number 2. And that electron can travel a distance that requires 8 kilojoules of energy required to make the electron travel that far. It's similar to the way you would measure energy, and we do this in my physics classes. How much energy did you put into a ball? We go out on the field, we throw a ball. How much energy did you have to put into that ball to make it travel a certain distance? And we have a way to measure that even in high school physics classes. So again, here we're going to take the first electron, electron number 1, we're going to hit it with 20 kilojoules of energy. It flies a distance that requires 15 kilojoules of energy. So there was 20 minus 15, or 5 kilojoules of energy holding the electron to the atom. So now let's stop and analyze that. You put 20 joules into the electron. It flew a distance that required 15 kilojoules. So what happened to that other 5? Why didn't it fly a distance that it could have with 20 kilojoules? And that's because 5 kilojoules of energy was holding that electron, was the protons holding that electron to the atom. So of the 20 kilojoules of energy that was put into that electron, 5 of it was used up just to pull the electron away from the atom, not to make it move any distance at all, just to get it pulled away from the atom. That was 5 kilojoules. Now the other 15 then caused it to fly out into space and fly some certain distance that required 15 kilojoules. So 5 kilojoules is the ionization binding energy. Now that that electron is gone, let's say that we hit electron number 2 with 20 kilojoules. It can only fly a distance of 8 kilojoules, that requires 8 kilojoules of energy. So there were 20 minus 8 equals 12 kilojoules of energy holding the electron to the atom. The point is, the reason it's more for this atom than for the first electron. The reason it's more for this electron than the first electron is that there's no screening or shielding electrons. This is a first orbital electron, so it has a much higher ionization energy than an electron in the second orbital. So 12 kilojoules is the ionization or binding energy. Okay, that was a lot, and that takes care of our lesson. So what we learned about today was ionization energy, electronegativity, and atomic radius, as well as 2 experimental techniques that determine the mass of isotopes. That one, the mass of isotopes, and also the ionization energy of that's required to pull an electron away. Okay, so that takes care of this lesson. Have a good day.